Good morning, everyone. I'm going to present a sparse tensor benchmark suite for CPUs and GPUs. I'm Jiajia Li, a research scientist from Pacific Northwest National Lab. This work is collaborated with other colleagues. Now let me first show our motivations. Tensors are multidimensional arrays which have attracted broad attention from diverse applications, such as deep learning, chemistry, social networks, and healthcare. This work we propose a parallel sparse tensor benchmark suite, which presents a set of reference tensor kernel implementations and consists of different workloads. Our objective is to provide insights of computer platforms from sparse tensor view and to obtain performance influential factors for performance tuning work. Now let me introduce the components of our benchmark suite. First, tensor operations. We have 5 fundamental tensor operations attracted from various applications. The first two are element-wise operations between a sparse tensor and a scalar or another sparse tensor. So these element-wise operations include multiplication, division, addition, and subtraction. These two kernels are simple kernels, but commonly used in deep learning and quantum chemistry. Then the kernels TTV, which is a tensor times a vector. TTM is a tensor times a dense matrix. They are a single tensor product because they only include one multiplication operation inside. TTV is widely used in tensor regression method in machine learning. MTTKRP is a sparse tensor times multiple matrices, so thus we call it multiple tensor product. MTTKRP is the most complicated kernel in here. TTM and MTTKRP are widely used in tensor decompositions in machine learning, and also among with other wide applications which use tensor decompositions to decompose their data to do better compression and more analysis. Well, among these 5 kernels, we have from the top to bottom, the time complexity increases. So we do some analysis on these 5 kernels from the number of floating point operations and from the number of bytes of the memory access. So you can see from here, the number of flops is growing from the top to bottom. Well, we compute operational intensity by dividing these two and achieved these values. From here, you can see all these kernels have the OI value smaller than 1, which means they are all memory-bound kernels on the state-of-the-art hardware architectures. Besides, we observed that different kernels have different operational intensity values. That is our motivation to get these 5 kernels to distinguish the performance in our benchmark suite. Now let me show our sparse tensor representations. Sparse data are usually represented in compressed data structures. We show a small tensor, very small tensor here, 3 by 2 by 3, with 6 non-zeros represented as dots. Now, serial format is a very simple format, which is short for coordinate format. So in serial format, every non-zero represented its non-zero value along with its IJK indices. So for the 3-dimensional tensor. So then similarly for the other non-zeros. So then we got a list of the tuples here. This is serial format. Serial format is also still popular in tensor libraries. Well, this is a HiCOO format, which is short for hierarchical serial format. It stores a sparse tensor in units of small sparse blocks. We use the same example here with the block size 2 by 2 by 2. By block, we first do a partitioning on this tensor. Partition this tensor to 3 non-zero blocks. First, the red subtensor here represent the block 0. Which corresponding to 3 non-zeros inside, which is the first 3 non-zeros in the serial format, and correspondingly, we will show them in the HiCOO format as well. Then the HiCOO format, the difference from the serial format is we have two levels of indices: block indices, the green area, and element indices. So for in CO format, the indices all use 32-bit for each of them to represent the indices. While for in HiCOO format, the element indices only use 8-bit integers to represent each of them, EI, EJ, or EK. In this way, we shorten because of the given block size, we shorten the bit length of each element indices to compress more space of the sparse data. While for the block indices, we still use a 32-bit as in the CO format, but we have less number of blocks than the number of non-zeros here. We only have 3 blocks versus the 6 non-zeros in the tensor. So in this way, generally, HiCOO format will get better compression compared to CO format. So, but there is a special case for HiCOO format. So if the tensor is hypersparse, which is really, really sparse, then in the blocks, it could be only one non-zero included in a block. Thus, you can say the block indices plus the element indices will consume the more storage space than the CO format. To solve this issue, we proposed another format. So please refer to more details for HiCOO format in this paper here. Thus, in this paper, we proposed the HiCOO format, which is a mix of CO format and HiCOO format. So for a sparse tensor, the sparsity among different modes, among different dimensions could be very different. So if, for example, here we have k dimension is very sparse, hypersparse, then we do not compress this dimension. So we just keep it as in the CO format here. But for the other I and j dimension, we still do the same blocking as in HiCOO format. So thus we got to the HiCOO format for sparse data. Now we introduce also the semi-sparse data structures. Semi-sparse tensors is a sparse tensor with dense modes, or dense dimensions. We give an example 3 by 2 by 2 tensor here with the k dimension as sparse. That means every fiber or every array along with the k index are dense. So that means we do not need to save the k index in the structure. So we include the SCO format here, which is introduced in these papers, and just use the dense arrays to save the dense modes. Well, in this work, we propose the HiCOO format for semi-sparse tensor. Similarly with here, we do not save the k index, so we don't have the bk or ek here, but use dense arrays here. Now let me introduce the dataset in our benchmark suite. We have 2 types of datasets. The first is the real tensors from real applications. So these real tensors included in our benchmark suite is a combination of the state-of-the-art sparse tensor collections work. Well, for the symmetric tensors, which is proposed in our work here, we extend the power law graph generator to high-dimensional tensors. So there are 2 types of tensors we use. For cubical tensors, where each dimension has the same size, we use the Kronecker graph model. And for the irregular tensors, which has different dimension size, we use the power law generator to extend and then generate our sparse high-dimensional tensor here. So overall, we get 15 sparse tensors from our synthetic generators, and with the non-zeros up to 100 minutes. Now let's show our experiments on our benchmark suite. We used 4 hardware platforms, 2 CPUs and 2 GPUs. So this CPU here, we have NUMA structure with 4 sockets. Well, the maximum peak performance we can get is on the NVIDIA. We have 100 GPUs, which is about 15 teraflops, and the peak bandwidth we can get is 900 gigabytes per second, also on NVIDIA V100 architecture. Then we use the Roofline model, which is very popular to get the performance upper bound. We draw this model, we only show this model here on the 4-socket CPU and on NVIDIA V100 GPU. All the file figures can be found in our paper. So let's first see the Roofline model on the 4-socket CPU here. We marked our 4 kernels as here as a different because due to their different operational intensity. So we found the operational intensity from x-axis, and then these lines crossed the DRAM memory bandwidth line rather than the peak performance line. So this means all these kernels are memory bound, as we analyzed before. So if we want to calculate the maximum performance these kernels can achieve, we use the tested DRAM memory bandwidth and then times with the operational intensity to get the roofline. Also similarly for this figure on V100 GPU, these kernels are also memory bound on GPUs. Well, the red line here shows the roofline performance we calculated as in the Roofline model. So now we got our first observation. Performance is generally below the Roofline performance calculated from the main memory on CPUs or global memory from GPUs bandwidth, except for some small tensors fitting into caches or algorithms. So we show different kernels here, T, W, and TS, which are the 2 simplest kernels. Then you can see the Roofline performance. Some tensors can achieve very close to the Roofline performance, also for the TS. So this means our Roofline model is accurate for these 2 kernels. Well, for the most complicated MTTKRP kernels, the performance is largely below the Roofline performance. We only can achieve about less than 20% of the Roofline performance, which is our upper bound. So in this case, this means MTTKRP kernels still have a lot of space to optimize. And we also need to refine our kernel maybe according to the MTTKRP algorithm's behavior. Now the second observation we got is it is hard to obtain good performance efficiency for non-streaming kernels on multiple socket CPUs, even harder than GPUs. So let's compare the 4-socket CPU result on tensor times matrix TTM here. So the Roofline, the peak performance is look as here, where there is some gap, a large gap between the performance we actually obtained from our kernel was compared to the Roofline model. Well, on the V100 GPU, there is still some gap between them, but you can see the gap on the V100 GPU is smaller than the gap on 4-socket CPU. So that means sometimes on some kernels on new architecture, it is harder to get performance than even on GPUs, but it also depends on the different kernels and the different kernel behavior. So this is very interesting. Maybe we need to pay more attention to optimize on the 4-socket CPU as well. So the third observation we got is the comparing between the data structures. So we use a HiCOO and the COO format, so different data representations. So from this data, we show that HiCOO algorithm shows more advantages for multiple mode operations, which is MTTKRP is the most complicated one, because of its better locality and smaller memory footprint. So you can see here, compared to the COO, the blue bars versus the purple bars. So our purple bars can achieve like 2 to 3 times speed up versus compared to the COO format. So that means when we choose the different data representations, we need to consider which one, particularly for which computational kernel. So if this kernel is for TTM, also for other kernels, maybe HiCOO could not, COO could behave a little bit better, or they behave similar. Most of the time, actually, they behave similarly. For the performance and observations, we also observed the achieved performance is diverse and hard to predict. We compared the performance between the two datasets, the real tensors and the synthetic tensors. For real tensors, we still use the TTM kernel as an example. The real tensors, the Roofline has some trend, but it's not this does not match well with the achieved performance from the real data. While for the synthetic tensor, it matches better than the real tensors. This is because our synthetic tensor, we can have much better control on the dimension size, non-zero pattern, and so on. So in that case, synthetic tensor will be helpful for performance tuning and also for compiler people to work on find out the reason for the performance drops reason or so on. So that shows the usefulness of the synthetic tensors. Well, one more observation is the synthetic dataset is also easier to expose performance trend, as we already mentioned. And this result is to compare between different architectures. So we compare between the P100 GPU and Volta V100 GPU. So you can see the TTM, because this is a memory bound, and the Volta V100 has higher memory bandwidth than P100. So then our Roofline model get higher performance than the Roofline model on P100. Well, also the achieved performance is still also higher, almost twice, sometimes almost twice. For example, for this one. Yes, this one is less than twice, but like 30%. So it grows a lot. Performance also increases along with the increased more memory bandwidth. So this shows the importance of also the synthetic data set. When we want to identify the hardware architecture bottleneck, or we want to observe which architecture will get better performance for this algorithm. So this will be useful for us. Now to summarize, we got our benchmark suite is extended from our previous past work. And in our benchmark suite now, we consist of 5 sparse tensor operations and also 5 sparse tensor formats. And with 2 datasets, one is a real tensor, one is from our synthetic tensor generator. And also we got 4 Roofline models for different hardware architectures. And from here, we observed the different patterns by comparing different tensor operations, different tensor formats, and also comparing the real dataset versus the synthetic dataset, and compare different platforms. So these operations could be helpful to get the performance tuning people, and also to study the algorithms to do further performance tuning, or to check if more insights of the architecture. So in the future, we want to test more on the sparsity support of the NVIDIA Ampere V100 with tensor cores, and also want to explore more architecture to refine our Roofline model, and also to see how much more architecture feature our benchmark suite can reveal for users. So our code can be found in this link. And if you are interested in more sparse tensor research work, please find them on my personal website. Also, I'm very thankful for the collaboration with the University of Utah, Purdue University, and Boise State. Thank you for your attention. Please reach out to me if you have any questions.